Hello everyone. Today I am going to deliver a lecture on measurement and prediction of welding induced distortion. So, this is the content of today's lecture. First of all, I will introduce how to measure residual deformation, that means you can say distortion. Then what are the different methodologies generally used for prediction of distortion. I will also discuss about experimental measurement of distortion, and also I will discuss about what are the different numerical methods generally used for prediction of welding induced distortion. The methodology for prediction of distortion in this slide I am going to show. We can predict, or you can say measurement of distortion by following way, like we can measurement the distortion by different types of experimental method. We can predict the distortion by some analytical method. We can also predict the distortion by some numerical method also. So, in numerical method generally what are the different types of procedure generally we used to follow, that I am going to show here. Here you can see that for prediction of welding induced distortion by some computational means or by some numerical means, you can say, which is nowadays is very popular technique, like finite element method is one of the most popular technique for prediction of welding induced distortion as well as welding induced residual stresses. So, this one of the numerical method related different techniques I am just going to show here. We can predict the welding induced distortion by using thermo-mechanical analysis. We can measure this, or we can predict this welding induced distortion by using inherent strain method. Generally thermomechanical analysis method is very high computational time consuming analysis. That is why what happens for large types of structure, this thermomechanical analysis is not feasible types of process. That is why to predict the welding induced distortion for very big structure, or you can say very large structure like a block of a ship hull structure, very big building structures. Generally for that to predict the distortion, generally inherent strain method is popular, which is generally computationally feasible and possible technique. Here the computational time requirement is very less. How it is, that also I will explain in subsequent slide. Another method is called average plastic strain method, and some other techniques also which are popularly used, that is called equivalent loading technique. Now, whatever the techniques name and procedure I am showing here, once you go through the literature about these different techniques related thing in details, you can find over there. Because in these lectures once I will go for discussing each and every techniques in details, then what happens, each and every technique will take one lecture. That is why briefly I will introduce about all these techniques here, but details you can get, more details you can get from published literature. So, these are the different types of experimental measurement method. Like what happens, there are different types of measurement method we can use to predict the what we can say measurement of distortion. Like we can use measuring tape to measure the welding induced distortion. Actually in welding induced distortion, it is generally either some shortening of length, or you can say shortening of width is taken place, as well as some angular type of deformation is taken place. So, these types of angular deformation as well as this shortening of this width and length we can measure by some measuring tape. Then we can measure by using some straight edge set, or we can say we can use by we can measure it by using some ruler. We can measure it by using dial gauge. Then some other technique which is called 3D CMM, that means 3-dimensional coordinate measuring machine. This CMM means coordinate measuring machine, which is popularly used for measuring the coordinate by which we can predict the welding induced distortion. How it is, that also I will show you in subsequent slide. We can measure the distortion by using some instrument whose name is LVDT. The full form of LVDT is linear variable differential transformer, or sometimes it is called linear variable displacement transducer. Okay. So, different nomenclature is there in LVDT, but it is more commonly used linear variable differential transformer. Okay. Then some other technique, that is called photogrammetry technique. So, whatever the techniques now I am going to show, these are all non-contact types of techniques. that means photogrammetry techniques is a non-contact types of technique. Then laser interferometry technique, this is also a non-contact types of technique to measure the welding induced distortion. We can measure the welding induced distortion by low power laser beam triangulation. Then we can measure it by using optical 3D scanning technique. We can also measure it by using high speed pulsed digital holography method. We can measure this welding induced distortion by using stereoscopic video imaging system also. So, these are the various types of welding induced residual deformation measurement techniques by which we can measure the welding induced distortion. So, once you know this different name itself, so at least you will get the idea by which we can measure the welding induced distortion. That is why I am showing different name in a single slide. Okay. Now, I will show in details about all this measurement technique. Like first of all, you can see by using this shortening of length or width, these types of things we can measure by using measuring tape that I am showing, like here this transverse and longitudinal types of shrinkage we can measure by using measuring tape, which I am showing in this figure. You can see once in a welded joint, if there is occurs some angular deformation, that angular deformation, like you see these types of angular displacement theta, once it occur, this also we can measure by using some ruler or straight edge set. Okay. This is generally ruler types ruler or straight edge set. Apart from this thing, we can measure this angular distortion by using some other means also, by using either coordinate measurement machine as well as LVDT machine also we can measure this angular deformation. How it is, that also I will show you in subsequent slide. The next is measurement of distortion. Here how to by using dial gauge. This is a very important instrument, you can say, which is very low cost instrument, which is commonly used for measuring the bending distortion as well as angular distortion by using dial gauge. You see, this is a dial gauge instrument which I am showing, and it has a magnetic stand, you can see. By this magnetic stand we can fix it in this metal wall which has magnetic property. So, you see, by using this magnetic stand, generally we can fix this instrument. After that, you see it has a probe, you can see this probe can move upward and downward direction. So, depending upon this linear movement upward and downward direction, here in this gauge there is a scale. By a scale we can measure the how much up and down or movement of this spindle is taken place. That dimension we can easily measure by using this indicator. Okay. Now, here you see, so by using this dial gauge we can measure different coordinate in different location. After that, generally we can get a idea, that means how the deformation is taken place over the entire welded specimen by measuring the coordinate by using this dial gauge. So, for that, what are the things required to do, little bit I am explaining, then it will be more clear to you. So, this dial gauge generally used for measuring bending as well as angular deformation also, like here you see this dial gauge, here it is set. After that, you see this dial gauge here it is set. After that, what happens, this by this dial gauge generally if there is some bending occur, then these dial gauge indicators generally give you some other reading. Without bending, it will give some one types of reading. After welding, whatever the deformation is taken place, after that once we measure again by using this dial gauge, it will give some other reading. So, before welding and after welding, whatever the difference reading we get, if we subtract from each other, then we can get how much actual deformation is taken place. Like here you see, we know, let this is a little bit I am giving you some example. Let this is a plate which we are going to weld. So, let in this direction we are going to weld. So, before welding it is, you can see, horizontal in nature. So, before welding we will measure this different coordinate. Let this is, we just mark some location in this plate. we mark some location in this plate in different position. So, after that, so before welding we will measure this coordinate vertical position by using this dial gauge position in a fixed place. So, after welding, once we what happens after welding, due to this shrinkage force, there can develop some angular deformation like this. So, whatever the predefined location or predefined point we marked in the plate, in that same location we will again measure the coordinate by using this dial gauge. So, after that, what happens, once we subtract this means a preliminary reading with this final reading after welding reading, then we will get how much displacement or deformation or distortion is taken place in different location of that welding plate. So, what happens, depending upon our requirement, we can measure either vertical displacement as well as we can convert this vertical displacement by angular term also, because what happens, we know if we know this and these coordinates, these different coordinates, then what happens, we can easily find out what is this vertical displacement. So, we know this horizontal displacement also. So, what is the angle between these two, we can easily measure. So, the both angular as well as linear displacement, vertical deformation also we can find out. Now, in case of some pipe welding, how to measure the deformation over there? So, there generally whatever the shrinkage effect is taken place in case of pipe welding, that expansion and contraction phenomena, whatever the things taken place due to welding in pipe types of welding or spherical types of specimen, there generally we can use string. This string generally wrapped around it. So, before welding we will wrap it and we will measure the length. After welding again we wrapped it, and the difference of these two will give us the actual distortion or deformation, you can say. Now, the measurement of distortion by using LVDT. So, I have already told you this is a very popular types of instrument, you can say. Here I am showing how the LVDT probe is look like. Here you see. So, here one thing you can keep it in mind, it is a common types of electromechanical transducer that can convert the rectilinear motion of an object to which it is coupled mechanically into a corresponding electrical signal. So, here what happens, it has a rectilinear motion, like what happens, this probe can move upward and downward direction. So, due to this movement on upward and downward direction, here generally we use some transformer types of winding system. What I am telling, understand. So, here generally this is core stand, you can see. So, here at middle there is use primary coil, and both sides generally we use secondary coil. Here you can see in this figure. So, this is secondary coil, this is secondary coil, okay, and primary coil generally used in middle portion. So, what happens, once this probe generally this probe is connected such a way it can move, here is some spring system is there, it can move upward and downward direction once we press it in a surface. So, you see, once we just push it, it will go back. Then what happens, once we again just release our pressure from there, it will return back to its original length. So, due to this motion of this shaft, you can say, this is generally this bar types of shape is generally called shaft. Once this shaft moves within this coil, so there is develop some voltage difference. And due to this voltage difference we can calibrate in terms of displacement. So, depending upon this calibration, that means depending upon this movement of this shaft, we can measure the voltage difference. That voltage difference we can correlate with this displacement. From there we can easily predict the how much distortion or deformation is there. So, here generally for that, so what are the principle of this LVDT? The principle of this LVDT is similar to principle of a transformer. This you should keep it in mind. So, you see here also use primary winding, secondary winding. Through this generally once this shaft move, then there is occurs some electromagnetic flux difference. That flux difference creates some voltage difference. That voltage difference generally we record by using some instrument. Here you see, this is generally called recording device, which display the displacement because there is a relationship with voltage difference and what it is called linear displacement, by which we can easily measure the deformation in different location. Here you see, so this is called LVDT instrument. So, what is the process here happen? Here generally rectilinear motion is converted to some electrical signal. That means rectilinear motion converted to some voltage changes, that voltage changes we calibrate in terms of displacement. Okay. This you should keep it in mind. So, this is generally popularly used to measure welding induced distortion, especially for out of plane deformation. Out of plane means angular types of displacement, which is not within the plane. It once the shape changes taken place, due to this shape changes, how the shape is occur, final shape is occur, that shape you can easily predict or measure by using this instrument. Now, we will discuss another types of what it is called distortion measurement technique. This is also a contact types of technique, because here the probe and the workpiece should contact each other, then only it will give a response of coordinate, what I am telling you. So, this LVDT, then this 3D coordinate measurement measuring machine, these are all contact types of distortion measurement technique. So, here there is a direct contact with probe as well as workpiece, then only we can measure the coordinate. So, this is also more or less similar to this LVDT instrument. Here is also used a shaft with a probe. This probe especially used which is spherical in shape, and it is generally made up from ruby types of material, okay, ruby material. So, that is why here I have written here, this probe generally it has a size is around 2 millimeter spherical types of ruby stylus. So, here also at the tip this types of ruby stylus is there, and it has also a similar types of principle, which is more or less like LVDT principle. Here is also one rectilinear motion converted to some electrical signal. From this electrical signal also we can measure the coordinate at different location, and by measuring this coordinate before welding and after welding, and if we difference this before welding with after welding data, we can get actual deformation taken place in the welded structure. Now, some other techniques which I am going to show now, which are generally all non-contact types of distortion measurement technique, like distortion measurement by using photogrammetry technique. This photogrammetry technique is a very popular technique. It is especially used for very large structural deformation prediction or distortion prediction. This photogrammetry, generally this word came from the Greek words, like here the Greek word photo related to light, gram related to relates to right, or you can say sketch, that means gram relates to the right or sketch, and metros generally means measure. So, these three terms generally combine together and make this word photogrammetry. Okay. So, by using this photogrammetry, we can measure the three-dimensional you can say deformation geometry of a very large structure. Okay. Because this thus photogrammetry is a process of making some measurement using here some photograph. Okay. Where a photograph can be referred to as a sketch which is made up of light, and it can also be used to produce, here it is written, map or 3D model of real life object. So, by using this photograph of the object, we can predict the what it is called real life 3D shape of that object, what I am telling. So, before welding and after welding, once we measure this, so we can get the difference will give us the actual deformation shape of that structure. Here that things here I have written, the dimensions of large structure, as I have written, a structure can be measured through the use of multiple digital photograph of the structure. So, first of all we have to take different photograph of that structure. After that, this photograph generally we process by using some widely applicable what it is called tool, you can say, or you can say widely applicable software tool which is generally used to find out the coordinate from that photograph itself. Like one of the very popular software which is used to extract the coordinate from the geometry or from the photograph is generally this photo modeler. This photo modeler software is a very popular software by which from the photograph itself we can extract the different coordinate. What I am telling this our required coordinates. So, by which generally before welding and after welding coordinate also we can extract from this photograph by using this software. So, from where we can easily predict what is the distortion taken place due to welding, because before welding we are measuring the coordinates and after welding also we are measuring the coordinates. So, once we just subtract these two, then we will get actual distortion or you can say deformation taken place in that structure. Okay. So, this for photogrammetry is a very popular technique mainly used for sheaf structural displacement or deformation measurement. Now, some other non-contact technique where like measurement by laser interferometry technique. Here this laser interferometry technique generally is developed in the Institute of Technology, Massachusetts. Okay. This laser interferometry measurement involve the use of both constructive and destructive interference among waves of light emitted from a single source. So, here generally what happens, whatever the interference phenomena taken place during the light emitted from laser to a object. So, once it emitted and fall into the object, then what happens from there, whatever the destructive and non-destructive types of interference phenomena taken place, by using this phenomena itself we can find out the coordinate change over there. So, by which we can easily measure the what is called deformation shape of that final structure. So, in this process here you can see this interferometry is such a technique. This technique generally should carry by following some precautions. What are those precautions? Because here always you should keep it in mind, here whatever the ambient light at which we should do this experiment, that ambient light levels should be low here, and there should minimal air convection current. What I am telling, that means flow of air over that region should be very minimal. What I am telling, understand? As well as this specimen should be vibration free. This also you should keep it in mind. That means vibration free specimen is required for both the specimen as well as interferometer. Then what happens, we can measure the reading more accurately. Now, another technique here I am going to show. So, I am just briefing about the different measuring techniques. So, I am not going in details of all the things, you just keep it in mind about its principle, then rest of the things you will easily be able to find out from published literature. This you should keep it in mind. So, here I am showing another distortion measurement technique, that is called generally measurement by low power laser beam triangulation method. Now, you know this triangulation method is a very popular technique which is generally used to measure the distance over a surface region. That means at different point distance over a surface region, that is very popular terms. And what happens, this is especially used for measuring the distance at different location. So, this measurement of low power laser beam triangulation, this method generally have the capability of measuring a vertical change. Here you see I have written vertical change in a plate elevation above a horizontal reference. What I am telling, understand, because once you do the welding, then there is occur some angular types of or out of plane types of deformation. That means it is this deformation shape is undulated in nature or different shape it can have. So, with respect to horizontal plane, how much displacement is taken place out of plane, that things you can measure by using this triangulation method. That things here we have written. So, it can measure a vertical change in plate elevation about horizontal reference plane by sensing a change in an established angular relationship among the system component. So, once there is some varying geometry with respect to horizontal plane, then what happens? Inside this what it is called system component, there is some established relationship. So, in this established relationship there occur some changes. So, that changes generally sense and finally, we can predict how much actually vertical displacement is there by using this technique. Okay. Here another things you should keep it in mind, to develop the prescribed geometry, the device needed to be positioned directly above the plate specimen. So, this device is generally used over the plate surface itself. So, to measure, that is why here it is written, to develop the prescribed geometry, the device needed to be positioned directly above the plate specimen. Now, another distortion measurement technique, this is also a non-contact distortion measurement technique, which is called a stereoscopic video imaging system. So, a stereoscopic video imaging system generally take the videograph of that specimen by using two different video camera. From left and right side, generally this video camera record the video image. This video image generally display in a generally single display surface. Okay. That is why here I have written this video image, generally the stereoscopic display system consists a single display surface, one which generally this left and right image are displayed. So, whatever the display we are getting from these two different camera, that is displayed in a single display system. So, from this single display system we can easily extract the coordinates by which we can easily predict the welding induced distortion. This is a very popular techniques, especially for a small scale distortion measurement purpose. This also you should keep it in mind, because what happens, this is especially used for a small scale distortion measurement purpose. And I have already told you, this stereoscopic camera system generally consists of a pair of video camera, which is mounted side by side to obtain left and right image, this which I have told you. Okay. So, this stereoscopic display system consists a single display surface on which left and right image are displayed, from where we can easily predict the what it is called welding induced distortion. Now, another technique which is also a non-contact types of technique, which is called high speed pulse digital holography technique. So, in this technique generally we use the principle of holography. We know in general holography is an interference method which is generally used for recording the light wave diffracted by an object, the object which is generally illuminated by coherent light. Okay. Which is this, you should keep it in mind. That means, once we illuminated a object by using some coherent light, due to this that means whatever the diffracted generally light wave are there, that diffracted light wave interference phenomena generally used to record the shape of that geometry. Holography is very popular nowadays, which is a very well known term nowadays, which is widely used in different advertisement purpose also. Okay. So, it is a measurement technique for out of plane welding distortion, which I have already told you. That means, compared to original shape, if the shape changes is occur out of plane, that things generally you can easily measure by using this holography technique. Here generally a complete deformation map we can get with a accuracy of around sub-micrometer level. What I am telling, understand, very good precision measurement it can give. So, from this deformation map here, whatever the deformation map we are getting from this holography technique, from this deformation map we can generate 3-dimensional deformed shape of that structure, by which we can measure the actual deformation of that welded structure. For that, always keep this thing in mind, whenever we will go for finding out the deformation, we generally have to first measure the original shape, after welding final shape. So, from there generally we have to subtract each, then whatever the difference we will get, that is the actual deformation or distortion. Now I will discuss some numerical method which are commonly used to predict the weld induced distortion. One of the method is called thermo-mechanical analysis. Thermo-mechanical analysis means here first of all we have to model the structure. In this structure we have to use moving heat source. By using moving heat source, whatever the temperature distribution is occur over the entire weld specimen, that temperature distribution generally we will used as a load in structural analysis, or you can say mechanical analysis. In that mechanical analysis, generally once we solve this effect of this temperature, then whatever the temperature changes, whatever the strain changes occur corresponding to this strain, whatever the stress change occur corresponding to the stress, whatever the distortion or deformation changes occur in that welded structure, that we can easily predict. So, here it is a structural analysis which is taken place by the application of temperature. That is why these types of techniques or these types of analysis technique is known as thermo-mechanical analysis, because here in mechanical analysis or structural analysis you can say we are using temperature as a input. This temperature is generally consists a transient phenomena. Transient, why it is called transient phenomena? Because this temperature is varying at a particular location. Temperature you can say is varying with time, because in case of welding, once you see how the temperature is varying in a welding process, like let this is your time, horizontal axis represent time, and this vertical axis let us represent the what it is called the temperature. Then you see during heating it is heat like this, and once this heat source move away from there, it is cool like this, and it is return back to its room temperature. Due to this heating and cooling, there is occur some expansion and contraction phenomena. And as it is a time varying phenomena, that means temperature is varying with time, that is why it is called transient phenomena. This you should keep it in mind. So, that is why this thermo-mechanical analysis also termed as transient thermo-mechanical analysis. Okay. So, here the basic governing equation used for thermal analysis, generally we use transient Fourier heat conduction equation, and for structural analysis we generally use stress strain relationship governing equation, which I have already discussed in details in previous lectures, like in prediction of residual stress. So, I am not going in details here again. So, this flow chart only, that same flow chart only here we are showing. So, by using this thermal and this structural analysis, we can predict the weld induced distortion. Now, this thermal structural analysis it can be sometimes we can use coupled thermo-mechanical analysis, where that means at a time we can combinedly do this thermal and mechanical analysis, and it can be uncoupled thermo-mechanical analysis. Uncoupled thermo-mechanical analysis means where first we will do the thermal analysis completely. So, after complete thermal analysis we will use this temperature data to a structural model. So, where generally there we will do mechanical or structural analysis. So, two different analysis we are doing separately, that means there is no couple types of phenomena here. This is called uncoupled transient thermo-mechanical analysis. Okay. Now, another way also we can do this analysis, that is called sequential types of coupling analysis. Sequential types of coupling analysis means like first you know in case of welding, generally welding heat source is a moving heat source. So, with time the heat source is moving gradually with this weld length. So, every small step of portion we can do thermal analysis. That thermal data we can use, that small thermal analysis data we can use to a structural model, where we can do the structural analysis. After that again we will do another portion thermal analysis, like this is one portion, second portion, third portion, fourth portion, fifth portion. So, a small portion thermal analysis, side by side a structural analysis. So, sequentially. thermal structural. So, a small portion thermal analysis, that part we will do for structural analysis. Again thermal analysis, that part we will use as a thermal load as a structural model. So, there again we will do the structural analysis, and finally this way we can complete the whole analysis. This is called sequential types of coupling analysis. So, sequentially we are doing the analysis. So, there are different types of way we can do this analysis, that I am just showing. So, what are the different way? So, different way, one is called coupled thermo-mechanical analysis, another one is called uncoupled thermo-mechanical analysis, third one is called sequential types of coupled thermo-mechanical analysis. Okay. This you just keep it in mind. These details I have already discussed in previous lecture. From there you can got the idea about these things. Now, you see that what is the tangent thermo-mechanical analysis. I told this tangent thermo-mechanical analysis generally is a highly time consuming phenomena, because in that tangent thermo-mechanical analysis process, here the time required is very high. You can't imagine for solving a thermal as well as a structural model of a dimension of 300 by 300 millimeter size. You can't imagine the time required is around 4 to 5 hours. What I am telling, understand? Now, if the dimension of a structure is 10 meter, 5 meter length, okay. So, this big structure generally by using this tangent thermo-mechanical analysis process is not feasible, or you can say is not computationally economical. Okay. For that there can be required very high super types of computational facility. So, for that reason generally for very large structure we generally develop some equivalent techniques, you can say. By using these equivalent techniques we can predict the overall distortion of a very large structure whose dimension can be 10 meter, 15 meter, like this, like in a ship hull structure, like ship deck structure, ship side hull structure, then bottom deck structure. So, different structures where generally welding is a very major phenomena for joining the stiffener over the plate. So, that is why what happens there, to predict the distortion is very much essential. So, for predicting that distortion, this tangent thermo-mechanical analysis is not feasible. That is why some equivalent techniques we use. So, one of the technique is called finite element inherent strain method. So, finite element inherent strain method. What is inherent strain? Inherent strain generally you can say are the residual plastic strain which generally are caused in welding due to complex means heating and cooling cycle. So, due to this nonlinear heating and cooling phenomena, whatever the plastic strain develop in the weldment zone, that is generally called inherent strain. So, this inherent strain generally exists in the weld and in its near vicinity. So, it is generally closer to the weld and its near vicinity where generally the temperature goes some large thermal cycle. Large thermal cycle, so that means it is closer to welding zone only. Okay. These strain are considered as a source which cause distortion. So, here this inherent strain method is a very popular method which we can use in finite element method for welding distortion prediction, which is generally computationally feasible and very efficient method. Now, here I am just going to show you the concept of inherent strain. We know in case of a welding, or you can say heating and cooling phenomena, during heating phenomena the total strain in case of welding we can represent by combination of this is the total strain. So, total strain we can represent as elastic strain, that means epsilon E is elastic strain, epsilon P is plastic strain and epsilon TH is thermal strain. The other different strain component are there, but these are the major strain component. That is why here I am showing this thing like swelling and other things, hardening, a lot of other component are there that I am not considering here. So, these are the major components. So, total strain we can represent like that, elastic, plastic plus thermal strain. So, this thermal strain generally once the temperature return back to its original room temperature, at that time generally this thermal strain converted to elastic and plastic strain, or you can say, we can say like this, since the thermal strain disappear when the temperature return to room temperature after the thermal cycle. So, the total strain we can represent in terms of elastic strain plus plastic strain. So, that these things here I have shown. So, total strain we can represent it as elastic plus plastic strain. Now, whatever the plastic strain we are getting, this plastic strain we can write as total minus elastic strain, that I am showing. So, this plastic strain which is called inherent strain, this inherent strain we can write as total strain, because this from here itself we can write plastic strain is equal to total minus elastic strain. Now, I have already discussed that this elastic strain is responsible for what? Elastic strain is responsible for residual stress. So, that things only here I have written. So, this elastic strain is responsible for residual strain, and this total strain is responsible for residual deformation or distortion. This you should keep it in mind. So, what you can say, this inherent strain is responsible for both residual distortion as well as residual stress. Now, I will show you how to predict this inherent strain, because this is a very popular technique by which we can predict the what it is called welding distortion for very large types of structure. That is why here I am giving basic concept of these techniques. Rest of the techniques I will not go in details, because the rest of the techniques you can easily be able to find out from published literature. So, here I am just showing this one techniques calculation in details. So, this inherent strain generally once we do the welding, correct, once we do the welding. So, in case of let us here we are doing the welding. So, due to this welding, so due to this welding, you see this welding direction is generally called longitudinal direction. This is let us x direction, and perpendicular to the welding direction is called y direction. Okay, this is called y direction. So, that is why what happens, this inherent strain we can categorize into two different categories. One is along the weld line, which is called longitudinal inherent strain. Another one is perpendicular to the weld line, which is called transverse inherent strain. We can find out by a constant k into q. What is this q? Here q you should keep it in mind, q is equal to your heat per unit length. Here unit is joule per millimeter, you should keep it in mind, its unit is joule per millimeter, or you can say meter, whatever it is. So, this q unit, how the joule per millimeter you are getting, that means heat input per unit length. This we generally can calculate by using this following formulation. We know voltage into current with efficiency, once you multiply, this will give us the unit of power. Voltage into current is generally power, its unit is we know watt, and if we just divide this thing by Ws means welding speed unit is millimeter per second. So, this watt we can represent as joule per second, and divided by velocity means millimeter per second. So, this second will cancel out. So, it will give us joule per millimeter. So, this q represents joule per millimeter, and this k, whatever the constant here I am showing, this is generally material property dependent constant. This k has a unit, this k unit is generally what it is called, this k unit is a millimeter cube by joule, that I will show you. So, for longitudinal strain intensity, or you can say longitudinal inherent strain intensity is represented as k into q, and for vertical, or you can say transverse inherent strain, or you can say transverse inherent strain intensity is represented as beta into q. Now, what is this k and q? This k and q depend on material property as well as plate thickness. Here I am just showing this k and q value. This k and q value generally k is varying from 0.255 to 0.335. You see, I have already written this from thick plate to thin plate. For thin plate its magnitude is more, for thick plate generally its magnitude is comparatively less. So, lesser the thickness, magnitude of K will be higher side. So, this is actually alpha by Cp. What is the unit of alpha by Cp? Here you can see what is alpha. Alpha is called thermal expansion coefficient. Its thermal expansion coefficient is unit generally you can say divided by that means 1 by K you can say thermal expansion coefficient. Then C is unit is generally joule per kg Kelvin, and this density rho is unit is generally kg per millimeter cube, you can write millimeter cube. Now, this kg cancel, okay, this kk cancel. So, what are the unit here you can get millimeter cube by joule. So, alpha by Cp is unit you are getting millimeter cube by joule. But in previous slide you have seen we have find out the Q unit. So, this K into Q if you just multiply, what are the things you are getting? Millimeter cube by joule and joule by millimeter. So, you see, so this KQ have a unit which is actually you can say meter square. This is actually you can say this whatever the things I have shown you, this unit actually this Vx unit should be area square. So, here the total volume of inherent strain in longitudinal and transverse direction generally can be related to the rate of heat input Q as below. Okay. Here I am showing. So, the total volume of inherent strain in x direction is represented as Vx is equal to K into Q and Vy equal to beta into Q. Okay. Now, this K and beta, this unit of this Vx and Vy, always keep this thing in mind, its unit is generally we will get as meter square. How the meter square you are getting, that I will show, because you can see this Q has a unit of joule per millimeter and this beta have a unit whose unit is generally here you can see meter cube by joule. And now we will just divide this strain intensity with a area cross sectional area, with a cross sectional area. This cross sectional area we should consider that area which is near the welding region area. So, whatever the area we will consider for finding out this longitudinal strain, that area here I am showing. Let this is the area, this black color represent the area which I am considering for finding out the longitudinal as well as transverse residual strain. So, whatever the area I will consider to find out the longitudinal and transverse residual strain, the same area we should consider for what? Once we go for applying this inherent strain as a initial strain in the plate to calculate the welding distortion, there also we choose this same area. For your convenient, here you can consider the areas which are equal to the fusion zone plus heat affected zones area. That is the area which are subjected to a temperature above recrystallization temperature. So, by using these things actually we can find out this longitudinal strain and transverse strain. This longitudinal strain and transverse strain, so once we impose in the required location of this welded specimen, by this we can easily find out what is the overall deformation of that large structure. Like here I am showing a large structure like the side shell or side shell of a ship hull. Here you see this side shell of a ship hull, its length is around 10 meter and its width is around 4 meter, okay, and it is comprises of different transverse and different longitudinals. So, once we apply this inherent strain over this welding area, whatever the area we consider for calculating this epsilon L and epsilon T, then what happens? By using these things generally we can easily find out this overall deformation. So, here you see, so for finding out this Vx and Vy, what are the things required? We required K and beta. So, this K and beta generally is a constant which is dependent on alpha, which is thermal expansion coefficient, C, which is called a specific heat, and rho which is called density. This you should keep it in mind. And similarly, this beta is also dependent on alpha by rho Cp, that means millimeter square. I have already shown this unit is generally strain by area square. Now, what is the unit of K here we are getting? So, K has a unit. So, K has a unit which is equal to your, you can say this alpha unit is 1 by Kelvin. The similarly C unit is joule per kg Kelvin, and density unit is kg per meter millimeter cube or meter cube, whatever it is, millimeter cube. So, this kg will cancel out, meter Kelvin will cancel out. So, K and beta has a unit which is equal to your millimeter cube by joule, millimeter cube by joule. So, whatever the Vx and Vy we are getting, from there we can easily find out what is the Q. Q is joule per millimeter, means heat input per unit length. So, we are getting Vx is equal to we know K into Q. So, K into Q will give us what is the unit we will get from here? We will get the unit is actually millimeter square, correct? This 1 millimeter will this. So, you see this Vx and Vy its unit is coming as millimeter square, or you can say intensity of inherent strain. This Vx and Vy is called intensity of inherent strain. Now, once this Vx is divided by some area Ai, what is this Ai? This Ai is the area at which generally we are considering this inherent strain. So, this inherent strain generally we consider near the weld zone and its near vicinity region. So, let us consider this area is, which I am representing, this black color here you can see. So, this area for a fillet joint I am showing this area of this cross section for calculation of this longitudinal inherent strain and transverse inherent strain. So, once we divide this Vx by using this cross sectional area, then we can easily find out this longitudinal component. Similarly, Vy by this cross sectional area will give us this transverse inherent strain. These things just you should keep it in mind. So, what are the things required to keep it in mind? That means, this whatever the area you should consider for finding out this epsilon L and epsilon T, in this area itself we should have to impose this inherent strain for actual calculation. Okay. So, in weld zone whatever the area we will consider for finding out epsilon L and epsilon T, so that epsilon and epsilon 2 T we should impose in this mass of cross sectional area, because generally in this cross sectional area throughout the entire length of the weld we have to impose this epsilon and epsilon T as initial strain. After that we have to solve the problem to get the actual deformation. This you just should keep it in mind. So, these are the references which I followed for this lecture. Thank you.